Hello, in this video we consider this typical example of conditional probability. We have two arms, let's just say boxes for simplicity. In A we have a total of 5 marbles, 2 of them are red and then 3 of them are blue. And then we have another box B, and in there we have 4 red ones and only 1 blue. The way Peter is going to select a marble is by first tossing a coin and then taking a marble from the box that the coin indicates in some way that he had already decided. The first thing we have to notice in a problem like this is that it would be a very good idea to draw a tree diagram, since we have one of those cases where something happens and after something happens, something else can happen. So what is the something and something? So the first event is whether Peter is going to select a marble from the box A or from a box B. And the problem says that he's going to toss a coin to decide that. And if nothing else is said, we're just going to assume that the probability of picking one or the other is a half or a half. So we're assuming that the coin is fair. After doing that, he's going to take a marble, and then there are two possible results. It can be either red or blue. For the box A, we have only 2 red ones, so the probability of picking red is 2/5. So the probability of picking blue is 3/5. And for the, oh, look at this B over here for blue is not the same as B coming from box B. So let's just write a bit more and call blue the second event. And as I was saying, selecting a marble from box B, red has probability 4/5 and then blue 1/5. Okay, so now we have a tree diagram. The first thing we want to determine is the probability that the marble is red. So that would mean that either he pick from the box A and pick a red one, or if he pick from the box B and pick a red one as well. So those are two separate events. Each of them could happen and each of them are good for us. So the probability of picking a red marble is going to be composed by summing the probabilities of the two events. For the first event, we have the probability of being half for picking something from the box A, and then we have to multiply by the probability of picking a red one, knowing that we are coming from the box A, which is 2/5. So we are multiplying along the branch, and then we sum multiplying along the other branch. So half times 4/5. So we have here 2/10 plus 4/10. So the probability of picking a red marble is 6/10, or if we want to write 3/5 to simplify. Okay, now the question does something very typical of this type of questions, where we now want to know what is the probability that the marble is coming from the box B if we know already that is red. When we did the tree diagram, what we use over here in this branch that I'm marking over here is that the probability of picking a red marble coming from box B is equal to 4/5. Now we are trying to find the probability of coming from box B, knowing that it's red. So we are switching the conditional probabilities, and we know that that's going to change the result. And we need to use the formula for conditional probability over here. So what we know is that the probability of any two events, just gonna call them E and F, of the intersection of any two events E and F is given by the probability of one of them multiplied by the probability of the other one, knowing that the first one is happening. And of course here we can interchange who E and F are, because the intersection of two sets does not take into account any order. So we could write instead that the probability of the intersection is equal to the probability of F multiplied by the probability of E, given that F occurs. So that's the basic formula that we have for conditional probability, and because from there we can isolate that the probability of, for instance, F given E is equal to the probability of the intersection divided by the probability of E. So if we try to apply this formula to our case with the marbles and the boxes, then we are going to have the probability of coming from B and being red, so the intersection of the two events, divided by the probability of red. And notice that probability of red is what we found on part A, and this is the typical structure of this kind of problems. We have the denominator because we found it on the previous part. So what about the numerator? Well, we can use the formula for the conditional probability, but this time using the probability that we know, the probability of red coming from blue. So what we know according to the formula is that we can find the probability of the intersection as the probability of one of the events. In this case, I'm going to pick the probability of B multiplied by the probability of R, given that B occurs. So again, what I do over here was to use the basic formula for conditional probability. I switch it around because I want to use what I know. If I make a mistake and instead I write the probability of R times the probability of B given R, then the probability of R is going to cancel between the numerator and the denominator. I'm not making any progress. So instead, I use the formula the way it works for me. The probability of B, so taking the marble from the box B, that's a half. And then the probability of being red, given that it comes from B, that's what I know already, right? That's what is given, because we know there are 4 red ones out of 5 in B, so that's 4 over 5. And all of that divided by 3 over 5. So sorry, I'm kind of running out of space over here, but then I have a numerator of 4 over 10 divided by 3 over 5. So 4 over 10 times 5 over 3. Cancel over here to say that this is 2 over 3. So I'm saying that if we know that the marble is red, the probability that comes from B is 2 over 3. And that makes sense with our intuition, because we can see that in B there are double as many red marbles as they are in A. So it makes sense to say that the probability of coming from B is 2 over 3. The structure we have just seen in this problem is typical structure of conditional probability exam problems. So I'm going to give you one more example of this type for you to practice, and then we are going to see a recipe for solving them all, no matter which person, Peter of whom, is selecting marbles or what. We're just going to see that all these problems, they kind of fit the same structure, and we can solve them all in the same way. So this is the example that I want you to solve. So you should pause the video and do it now. Let's look at the general case. We are considering a situation where we have two events happening. First, something happens. Let's call the first event A. Well, or if A doesn't happen, then A complement is happening. So let's say we know the probability of A happening. So probability of A, I'll write it here. And then we know the probability of A not happening. That's going to be 1 minus the probability of A. This is the first stage. Then something else happens. Let's call the second event C. So we know what is the probability of C happening given that A happens. So then we also know the probability of C not happening. So the probability of the complement of C given A. And C also could be happening after A complement. So then we know that probability. So the probability of C given that A prime occurs, and also C could not happen, so the probability of C prime given A prime. Okay, so we have two events, A, C. We have some information. The minimum information we need to know here is the probability of A, and then we need to know how likely C is to happen if we already know that A happens, and how likely C is to happen if we already know that A does not happen. So we have those pieces of information, and then the typical question is that for part A, we are asked what is the probability of C happening. And here we can see that there are two ways that the event C can happen. It can happen after A, or it can happen after the complement of A. So over here, for finding the probability of C, what we are looking at is the probability of C happening at the same time of A plus the probability of C happening at the same time as the complement of A. To find the probability of the first intersection, so A, C, we are multiplying along the branches, so we have the probability of A times the probability of C given A. And then for the second branch, we have the probability of the complement of A multiplied by the probability of C, given that the complement is the one that happened. If we want to think this in terms of Venn diagrams, we can imagine over here that we have our whole universe, and then we divide it in two parts. Either A is happening or the complement of A is happening. And then we have a second event, C, here, that can happen at the same time as A is happening. This will be the orange part over here. That's the first branch, and that's what we found here, multiplying the probability of A and the probability of C given A. Or we can have this green part over here, which is the second branch and is the second term on the sum. This is another way of looking at this. Now let's imagine that part B is asking us to find what is the probability of A happening given that we know that C is happening. So we are switching the conditional probabilities. We knew the probability of C given A, now we want to find the probability of A given C. According to the formula for conditional probability, we need to find what is the probability of C intersection A, and we need to divide it by the probability of C. And notice that the probability of C intersection A, we already found it, is the orange underline over here. And the probability of C, we already found it. That was actually what we did on part A. So if I want to spell out really what we have over here, we wrote that the probability of C intersection A is the probability of A times the probability of C given A. And then the probability of C in the denominator has the term I just wrote in the numerator, and also the other term with the complement of A. So this is how the formula looks like. And the reason why I wrote this down is that for the higher level students, this is actually a theorem. Bias